In this video, we're going to look at reflections in the coordinate plane. So we have the point A already labeled 3, 7, and it's been plotted. We want to find the image of A prime. So we're going to reflect it over the following lines. The first line we're going to reflect over is the x-axis, which we see is right here. So remember, the nice thing about reflections on the coordinate plane, you can just count. So I'd count the straight distance down from A to the x-axis, and that's a total of 7. So I would count 7 down. And that would be A prime. So that A prime is at 3, -7. We're going to do the same thing now for the y-axis. So we count to the left now 3 units until we're on the y-axis, and we go 3 more units to the left. So that version of A prime, or if I want to call it A double prime, would be -3, 7. The next line is x equals 6. Now remember, x equals means it's a vertical line because everywhere along the line the x value should be at 6. So that value is here. So same thing, we're going to count 3 units to the right this time so that A is on that line, and then we 3 units past. So that would be at 9, 7. And finally, we have one more point we're going to look at here. Y equals 4. So this is a horizontal line. So for us, for A to get there the most directly, we're going to count straight down 3 and straight down 3 more. And that point is at 3, 1. Okay. So while we look at the reflection over the x-axis, that's always just going to be a change in the y. It's really the opposite letter that changes it for us. So that would take xy and becomes x negative y. The opposite is true for when we reflect over the y-axis. That original point xy changes to negative xy. So with those two, it's like the opposite letters what's reflected because you're thinking about how it's folding over each other. Now we could create a formula for other lines like x equals 6 and y equals 4, but really if you have a graph or access to a graph, it's so much easier just to count. So you don't really have to memorize any of the rules here, just as long as you know how to apply them. So vertical and horizontal lines are easy to reflect across the coordinate plane, because it's rectangular. If I was looking at this diagram where we have point A has been reflected over the line M such that its image A prime is shown, points A and A prime have been connected to form A to A prime, which intersects the line M at point B. So what is true about A prime, and M? So let's first think about what kind of lines is going to be true and think about what we know about a reflection. Think about back to that do now, we counted the same distance in each direction here, like from AB and from B to A prime, they should be the same direction. So one thing that should be true is those are equal, but think about a reflection. Our line of reflection when we constructed it is always made by a very popular construction of ours, the perpendicular bisector. So we should know that A prime, and M are perpendicular, and those two pieces in particular are congruent because they're also going to be bisected. Now in the next part, C, it says only using vertical and horizontal lines draw the most direct path. Now we know the fastest path to a line is a straight line connecting it, but we're only using horizontal and vertical here. So I'm going to draw in a vertical line and then a horizontal line. And we're going to do the same thing again down. Now, what shape do we know is formed? Well, that would have to be a right triangle. So now if we were imagined to apply this reflection on the coordinate plane, what can we calculate by performing the same steps as part C? Well, think about what we did. We went down and over, down and over. We looked at the change vertically, so the change in y over the change horizontally. So we have a formal name for that. The change in y over the change in x is known as the slope. So we can always use the slope to help us calculate our reflections as well. Now you may recall earlier this unit, we talked about these two special lines. So if we had y equals x and y equals negative x, if I was to plot them, our first line y equals x, remember, we could start at the origin because there's no y-intercept and go up 1 over 1 and down 1 to the left. That's our line y equals x right there. And our slope's just 1, or 1 over 1. If we were to look at y equals negative x, same thing, that my y-intercept is at 0. So I'm going down and over this time, but down 1 over 1, because this time my slope is negative 1, because it's that number in front of x. Or again, same idea, negative 1 over 1. We can use that slope formula to help us. So we have my two lines, y equals x and y equals negative x. But these lines can be helpful for us if we were calculating a reflection of over these lines. So we knew when we reflected over the vertical and horizontal lines, we just count a straight line down or a straight line left and right, straight line up. Now we're counting vertically. So now these lines, y equals x and y equals negative x, it's not going to be the same exact thing, but there is a nice way to still do this. So let's look at the point negative 6, 2 that they gave us for A in this fourth example. We want to reflect over y equals x. So we can really do it any way we want to. So imagine calculating the slope. So I'm going to count 4 up to that line. Oops, just kidding. I'll come back to that one in just 1 second. I forgot I wanted to start with y equals x. So rather, I'm going to count down as my rise is going down. So I counted down about 1, 2, 3, 4, 5, 6, 7, 8. To get the reflection over this line, though, we're going to count 8 to the right now. That would be our A prime in this case. So that's at the point 2, negative 6. So we're calculating down. Now imagine if I folded my page along that line y equals x, that point would map onto one another. We would be happy with that. Let's try it again though, for the line y equals negative x this time. So that line is up 4, and I'm going to go to the right 4. Same idea now. If I fold it along this line, y equals negative x, I'm just going to call this a double prime, would be at the point -2, +6. So let's see if there's anything we might notice about the rules here. If I'm looking at y equals x, if I look at how the original point was -6, 2, and then became 2, -6, the only thing that happened is y and x switched places. Okay? So think of it. If we're reflecting over y equals x, you're just switching those points around. Similarly, when we flip over y equals -x, those points still switch, but they also change. So I'm going to have a -y and a -x. Because remember, they're switching signs. So that negative doesn't mean the point is actually negative, but it means it's changed from their original value. Okay? So when you have y equals -x, they switch the order like yx, and then the negatives to both. So now with exercise number 6, we're going to put back from the other video. First things first, we have this point -5, 3. So I'm starting at this point here. I'm going to reflect it over the line y equals x. So if you see this, you could automatically just switch your points to 3, -5. If you weren't sure, plot and count just like we did. Okay. And I could always fold my page along that middle line to see if that would work. But so far, that's the first part. But now we also have an and then rotated 90 degrees counterclockwise about the origin. So remember, just as a reminder, that starts as xy and changes it to -yx. And that means we'd have the point +5, 3. Choice 1. Okay. You could also turn your page 90 degrees counterclockwise to see if that point falls right there. So if that purple point, if I move that up, we are going to end up at 5, 3, right there. Okay. Looking at the final question, reflections in other lines can be a little bit more difficult, but the key factor is to think if we're reflecting over a line, we want the slope. And by when we connect them, they should be perpendicular, right? We talked about that perpendicular bisector being our line of reflection. So we have the equation y equals 2x minus 3. We have the point R at -2, 3. If R was reflected over line M to produce its image of R prime, what would be the slope of R to R prime? Well, we just talked about that in perpendicular. So my slope here was 2. My perpendicular slope is going to be a -1/2. Okay? We can write that the line of reflection is perpendicular. Okay, so that line of reflection of this line here, when we go over it, that connecting point should be perpendicular. So now we're going to graphically find the coordinates of R prime. So I'm going to use our slope. From R, I'm going to go down 1 over 2, down 1 over 2. Notice it took me 2 times to do it. So that means when I go past this, I'm going to want to do this exactly 2 more times. So I'm going to go down 1 over 2, down 1 over 2. The reason why it's going to be that same amount of the 2 different slopes applied is because we talked about the line being perpendicular and being a bisector. A line of reflection, is always a perpendicular bisector. So connecting R to R prime should have an equal amount on both sides and be perpendicular. So R to R prime is perpendicular to our line y equals 2x minus 3, and it's bisected. And our new point here is at 6, -1.